Right, John, can you see that all right?
Yep, no problems at all. The presentation is part 2 of the talk by VK OE title. And it's
the reason for that is that it's exactly 12 months ago that I did a talk here in this room on dishes and dish feeds. And we came up with a list from that discussion of a whole lot of extra things that we could talk about. So it's been a year and a bit of various other directions of life. But I've now done the part 2 version of it. So here it is. So basically, that first talked in some detail about prime focus and offset parabolic dishes. And the recording of it is on the Brisbane VHF group website for the world to look at if they want. And all sorts of different types of feeds, which actually ended up being quite an interesting thing, certainly for me, preparing it, but I hope for other people as well. Okay, so I already talked about this one being the other issues, the orphaned issues, which were cassegrain feeds for very deep dishes, multi-band feeds, in other words, feeds on more than one amateur radio band. A bit more on the prime focus dish versus the offset dish. These are the things we'll be looking at this evening. Position and angle of the feed, and particularly some comments about phase, center, and focus and things like that. Septum feeds for circular polarization. Mounting the dish, steering it, wind loading, and that'll pull up the end of it. Hopefully, it'll be interesting. So here we go. Cassegrain feeds. What are we talking about here? Instead of the feed coming through the back end of the dish, instead of the feed being out there in front of the dish, it's actually fed from somewhere near the back of the dish or behind the dish. And there's a little reflector which you can just see. Just give me a chance of moving the mouse around it. Yeah, this one here. So it's a double reflection thing, and you can see that looking at that picture that it's possible to get a good illumination of a dish that's where it's really very deep. Now, the extreme version of this is the Honeysuckle Creek thing near Canberra, 73-metre dish or something, listening to 20-watt transmission coming from 70 billion kilometres away, and getting quite a good signal and getting a signal back to them as well. This is a bit closer up version of the cassegrain reflector itself. You notice that it's obviously not parabolic. Talking about this white thing in here is in fact hyperbolic, which is the mathematical solution to a beam that's coming out here and then being reflected out here into this. Okay. I get rid of it. Good. And radio amateurs don't necessarily produce something that's absolutely perfect like NASA does. But radio amateurs do interesting things and get good results. So here is an example of a fairly deep dish being fed with a circular horn and then the cassegrain reflector in front. Here's a a Japanese one, look and see the what's that telling me? All right. There's the actual feed coming out the end of that little tube on some millimetre wave frequency, and there is a Cassegrain reflector that's carefully positioned at micrometer accuracy, and the signals coming out here being reflected by this and illuminating this dish, which actually doesn't look like it's very deep, but it's a way of doing it with a shortest possible waveguide feed. There is, in fact, Champion W1GHZ has an online Cassegrain antenna calculator, and here's the picture on the left there. Is similar to that one we have. It might be the same as the one we had before, but look at this one. Different dish, different parameters in the calculator, and there is a very deep dish being suitably illuminated by that feed. Amazing. I'm not going to try and go into the details of it. There's a lot of mathematics. If you like mathematics, there's plenty to wallow in mathematics of Cassegrain dishes, reflector dishes. So, multi-band feed. Here, with all the feeds we talked about last time, we're only really talking about single-band feeds. So what are we talking about here? We're talking about ones that work on 2 bands or even multi-bands. So we could look at horns, rings, log periodic, the Vivaldi feed. There's a 75 LUA long-time summer special for 5 gigs, 10 gigs. And W1GHZ recently released a design, and you can actually go and buy a really good one for 10 gigs and 24 gigs. So let's look at these and see where it's going. These horn feeds are not intended to be the main transmitting and receiving antenna. They're intended to be feeds in front of a dish of some sort. They're very broadband ones that cover wide frequency. Seem to rely on a kind of a taper that becomes wider and wider in the middle of the dish. You could say, yeah, Cole just said that's a Vivaldi in there. Here's the only diagram that I could find of something like that, but it shows the feed, one side being at this side of the kind of the circuit, the taper. I don't know if it's probably hyperbolic too. Would you say, Roger?
I think so.
And anyway, there are 2 of those there, and the feed is being paired across that little gap there, a bit like a slot antenna, or Alfred slot if you've ever made one. Oops. Here's another very broadband one with flimsy side panel. Commercial one you can buy for a couple of $1,000. Everyone needs one. It's platinum plated gold, is the comment from the Peanut Gallery. Here's an interesting one, which seems like it's mostly air, but it's a broadband horn of some sort. It could be used as a dish feed, or it could be just used in antenna testing or materials testing. I know this is not a dish feed, but I'm quite proud of this thing, which can operate on 10 gigs or 5 gigs or 3 gigs or 2 gigs. depending on which you take this part off and take the taper off and put a different transition in there, or take that all off and put a different transition on the end of the main horn. That's 2 gigs there. This is 3 and 5, and this is 10 gigs. So that's multi-band in a different sort of way. But because of the aperture of the dish, it's up in the same sort of league as a small parabolic dish. It does work very well. There's another type now we're talking about, letting horns behind, multi-band ring feed. Now, RF ham design in the Netherlands is the main instigator of these in the amateur radio market that I found anyway. And this one's got 4 bands all in one thing. You can buy single band ones from him or 2 bands. Name your frequencies, name your frequency or frequencies. And I know that Roger here's got some, and maybe other you fellas have got them too. But essentially you're looking at a 1 wavelength loop on each of these bands set in free space somehow or other behind a reflector that looks a bit like that. Quite interesting, and you can adjust that to be optimal on any frequency you like. There is some interaction between different rings, but RF ham design has sorted that out and made it possible to actually achieve reasonable results. I'm not selling them either. Yes, Andre asked you a question.
On the previous slide, if you just go back, talked about the 1 wavelength being in free space. Why?
It's suspended. The question is, with these rings, like that one, it's suspended there in space at approximately a 1/4 wavelength, probably a bit less, above that ground plane behind there, which has a collar on it that will minimise the dispersion. So this one here is for a higher frequency, the one in the middle. This one's for a lower frequency. But you imagine with this 4-band one down here, there are actually 4 rings inside the... Yeah.
And so because we're saying because it's a 1/4 wavelength, it appears as free space.
Well, yeah, a bit like that. It's actually not a 1/4 wavelength, but less than a 1/4 wavelength. In the same way that a reflector on a Yagi is less than a 1/4 wavelength away from that driven element. This is an old one. Got to be 30 years old, the design. At the time, I visited Tom Hill, WA3RMX. The world was marvelling at this design here. This is a double-sided printed circuit board. One side has hard to get it out of here. One side has this thing here, and then half of this antenna. The other side of the printed circuit board has a feed or 50 ohm line running up here, and then it's connected to these little whips, which tend to form dipoles on 3 different bands. And so it works on 2.3, 3.4, and 5.7 gigs. And then these are reflectors, all on one printed circuit board. Yeah. Cole just mentioned that there is a picture on the internet of someone running it up to a couple of 100 watts or something like that, and and looking at the charring of the what would you call it, the fiberglass substrate in this area. Yep. Yep. Now these are 3 reflectors. So they in fact focus the energy from these radiating dipoles back towards the dish, and the dish will be around here, right around there, so the whole thing faces back out to the right, but the feed itself is directing the energy back into the dish. I had one years ago, long before there were people around, on 3.4. Don't remember what happened to that. Okay, Kent Breton WA5 BJB, other call signs, has developed these log periodic antenna designs for different bands. This one here is showing 900 to 2,600 megahertz. It's a log periodic feed, so it's not like a Yagi. It's actually got one sort of operating area of the construction at one time. It's a log periodic antenna. There's a log periodic dish feed, which was home built by the late Wally Green at VK6WG of Roger will remember him very well. In the 1980s, was setting world records on microwave frequencies. And I don't know where he got all his information from, but it was all good. I visited him years ago, and just for the log periodic feed, fascinating. We're talking about these here, see the log periodic elements. What did you say, Colin? It worked, yeah. There's a smaller log periodic feed for 2.4 to 6 gigahertz. And here's a Vivaldi feed. And that's why Colin mentioned that when we were talking about those wideband horns. But in practical use, to actually bring some coax along here, solder the coax to this, that's free right through there. Solder the braid of the coax there and the center conductor here, and it just seems to work. I don't know why it works so well, but it's a little bit too flimsy to put permanently at the focus of a dish, but it works.
I just brought a couple of those in, actually got SMAs on them already done.
Oh, good.
It worked. Actually, I got one set up in the backyard, just hanging on a piece of coax, and the 23 centimetre beacon with S9 at home in the garden.
Yeah. Pretty amazing.
I swept it with the V&A and it's yet. Amazing.
So it's reasonably flat, you mean?
Yeah.
Good. Now, W5 used to be WA5, or WB5 anyway. A while for the world to realise that he was W5 anyway. Anyway, notable microwaver pioneer in the United States. But he developed this dual band feed for 5 gigs and 10 gigs. And it works really well. I've been using one of these for 15 years or something like that for my 5 gig and 10 gig portable station. So that's it, feeding a small sized dish. I believe it's intended more for prime focus dish a bit like this that's not greatly deep, that's all right. That'd probably be okay for offset as well. How that works is, I thought sure of that. If you look at this here, this is the 10 gig feed, which is circular waveguide transition from the coax, and then the wave front comes up here, and it strikes this flared section here with an angled section, making it a what do you call those, Roger? Dual mode feed. So the different waveguide modes that are happening in there now combined together at this point out here to make a nice even wave front coming out of the front of the feed. For 5 gigs, there's the feed for 5 gigs. The signal there doesn't go back down here because the waveguide is too small. So it just feeds it like a coffee can feed, and it directs the 5 gig signal out this way as well. I've been very happy with it for a long time, but I'm just changing over to a 5 gig dish right now. Here's a very good product that W1GHZ has available on the market. Optimized feed for 10G and 24 gigs. So there is the 24 gig waveguide feed. You'll see that picture. 24 gig waveguide feed. And here is the 10 gig input, which has a low pass filter built into this little built out section on the side. And the results are excellent. It's a low pass filter. Waveguide's 24. So what you don't want lots of 24 gig energy coming back out. There's the low pass filter. It's not your typical low pass filter. It's one of those ones with thin inductive transmission line with a couple of discs on there which form capacitors to the outside. Anyway, quoting W1GHZ, calculated efficiency was 76%. Now that's remarkable. And 74 at 10.3. Comparable to the best single band feeds. It's a dual band feed that does not compromise performance. I've got one of these at home, but I haven't used it yet. All right, we've spent a bit of time in the first talk talking about prime focus dishes and offset. Just so you know, we're talking about. There's a prime focus dish at VK4AFL a few years ago. There's an old VK4OE portable station with prime focus dish. There's an American there. You can read the call sign in the middle of the dish, work out who it is. But that's an offset dish of quite sizable proportions. And here's a much more manageable offset fed dish. Looks like it might be 24 gigs or something. So we talked about that, but just some general points that I didn't talk about before related to these, and that is an observer, if you're talking about a prime focus, an observer can easily see the direction a prime focus dish is pointing. And then it's also possible to sight across the front of the dish, get an accurate compass reading on it, and then add or subtract 90 degrees, get the actual reading. It works wonderfully well. an observer looking at an offset fed dish can easily be confused about where its main lobe is pointing. I often think about this when looking at satellite dishes on houses, and you get interesting things. Radio amateurs don't always have the dish in a vertical frame. That some radio amateurs turn it 90 degrees and have it sitting off at a funny angle. Some turn it completely upside down, and all right, yeah. Roger just mentioned that he has a 10 gig system with the feed at the top because the dish has been turned right around. Your offset fed dish. Whatever type you've got, they both require calibration exercise so that you know where you're pointing. Of other general points, or a prime focus dish feed will always partially block the main field reflected by it. This blockage is a blockage to the most efficient central area of the prime focus dish, which seems to be something you wouldn't like to happen. But when you work out the percentages of loss, it's usually not very great. It does affect things. But that reflection back into the feed can lead to, you measure the feed separately, and then you measure it located in front of the dish. You can get wildly differing measured results. The whole antenna compared to the feed due to this reflection back into the feed. And for offset fed dishes, blockage by the feed is not usually an issue. If it occurs, it's only minimal because it's near the outside of the main beam. So that's due to the fact that some offset fed dishes have the original focus, the focus of the original big parabola still as part of the reflector. I've got a couple of machined offset fed dishes that are a bit like that. This is like a little primer for the rest of the talk. Both prime focus dishes and offset fed dishes present the radio amateur with considerable mechanical challenges for both mounting the dish and being able to point its main beam in the desired and repeatable direction. The bigger the dish, the bigger the challenge. And some of you here have played around with these things. I know Colin's played around with a big one, folding the umbrella, which is a pretty clever thing. Okay, let's have a little bit of a talk about the position and angle of the feed in front of a parabolic dish of some sort. Getting onto the subject of phase center. The phase, this is the pure definition. The phase center is the point from which the electromagnetic radiation spreads spherically outward, with the phase of the signal being equal at any point on the sphere. The ideal doesn't ever get to exactly that, but that's what it's like. It's what we try to. But we should really be thinking about apparent phase center in one and other directional antennas, since the radiation is only emitted at certain angles. But there is an apparent phase center where it appears to be the origin of the field. So for radio amateurs, phase center of the feed needs to be located exactly at the focus of the dish. Does that make sense? If the feed and the antenna cover more than one band, note that the phase center within the feed differs between the two bands. may sound strange, but I mean, think about the mathematics of trying to get a field to propagate down some funny bit of strange waveguide or something like that. If you had 10 gigs and 5 gigs, they're going to behave quite differently. Or 10 gigs and 24, or 24 and 47 or something. Now, multiple feeds, meaning that you've got different feeds in front of the dish covering different bands. The EME fraternity quite often have, a feed, big, well, if you think of the late Doug MacArthur, A3UM, that big dish, he had a stack of DIA dipoles on 432, then a great big dual mode feed for 1296 right sitting in the middle of them all. It's crowding, but he's trying to keep the beam at the same location, so the same direction all the time when he flips between bands. But really, the satellite, TV satellite receiving fraternity, they have different feeds located at different positions in front of the dish because different satellites they're listening to are in different locations. But you do get crowding there if you're trying to get ask too much. The little rule of thumb here is to set up the feed position to favour the higher band, and then loss of performance on the lower band due to phase centre not being coincident should be minimal. So here, if you just look at that superimposed yellow markings on the log periodic, that will be the approximate phase centre for 900 megs. But if you go down to the other end of the spectrum, 2.6 gigs, it's going to be somewhere up near the front, which is quite a big difference. If you're using one of these to feed a dish on multiple bands, you're not going to get the same radiation pattern each time. Now, on that dual band feed from W5LUA, the phase centre is described as being about 1/4 of an inch inside the open end of the feed. Just 1/4 of an inch. Now, I presume, there was no comment about that, but I presume that that's on both bands. Yeah. What's happening there is that this dual mode flared out section changing the way that the fields interact, and approximately the same location there, which is quite different to the log periodic we just saw. And this marvellous feed here, again, W1GHZ's quoting here, the best front to back focus on diameter ratio and phase centres for the two bands are not the same. The best choice appears to be the chaparral horn, with a phase centre differing by only 1.3 millimetres between the two frequencies of use. That's 10 gigs and 24 gigs. The result is that the optimum position for 24 gigs is only 0.04 wavelength different at 10 gigs. Doesn't that make you absolutely amazing to achieve that? On the WA3RMX, the phase centre has been declared by all those pundits to be on this line, somewhere located in there. So that would be the focus of a prime focus parabolic dish. Some USAM radio emitters, when this feed came out, would just put the feed up in the air when they're mobile and talk to people that they're driving along the road with no dish, just the feed by itself. This seems like a fairly obvious thing, but you've got to get it right. Mounting the dish feed at the correct angle. Simply aligned for a prime focus dish, you just simply align it on the axis of the dish, with the phase center of the feed located at the focus of the dish. If it's an offset fed dish, again the phase center of the feed needs to be at the focus, but set it at an angle that the field generated by the feed evenly illuminates the dish with symmetrical spillover all around the dish, or symmetrical under illumination, if that's the way it is. Septum feeds. This is what the consideration here is. If you're planning an EME station from 1.2 to 5.7, at least, you'll need to be using circular polarization, and the septum feed will be one of the best go-to designs. What is a septum feed? Well, there's a picture of one in front of a dish. Distinctive sort of square tube arrangement. OK1 DFC. There's the same one looking again. So what's inside that square copper tube? There's the open end is up here, and in the middle of this, there's a partition coming in here with these stepped sections on it, and there's a simple probe coming in from one side for the transmit port, and a simple probe on the other side for the receive port. So if you're looking down into the inside of one of these things, I hope you can see, looking in there, you're looking into a kind of a blind-ended tube, or maybe 100 mils across or something. There's one of the probes for transmitting or receiving, and this one's the other one for receiving or transmitting at the same time. And there's amazing isolation, 60 or 70 dB isolation between one side and the other, if it's all adjusted properly. Here's that stepped partition. And all this, with that low loss, it really means that the connections to it are really easy. The transmitter can just be connected straight in there with no transmit-receive relay. And the receive port out here, and there'll be a relay. You know, even if you're running a kilowatt here, 70 dB down is still potentially able to damage an LNA. So dumping that into a resistor is a good idea when you're transmitting. Of course, lots of radio emitters use kilowatt, don't they? Okay, a septum feed can be improved by adding can be, but won't always improve antenna performance. A scalar ring front down at the open end. You might remember that first picture didn't have that on, but this one does. And this one certainly does as well. So the performance of this septum feed with a scalar ring is truly remarkable. Look how deep a dish this can go down to, 0.3, less 0.35 in that sort of area. And quite good turn loss and all that type of stuff. But look at the radiation pattern. I haven't seen a radiation pattern as good as that. Looking through all of W1GHZ's material. Look at that, just even feed right across from a big wide area, and then fairly well to retain in the back area. Good front to back ratio. Everyone needs one. Okay, we can mount the dish in different ways. First one is rigid, pointing in one direction. This, of course, is what commercial industry does most of the time. We radio emitters are funny lot because we want to be able to steer a dish or an antenna. Excuse me. So what are we talking about here? Pointing in one direction only. The azimuth elevation Azell mount and the equatorial mount. We're looking at mechanical considerations, wind loading considerations. I think that might bring up the end. Oh, yeah, just electronic versus how do you know which direction you're pointing is really what that line is going to be talking about. And if you've got a computer that you can organise to actually work the dish, that's a big advantage. Okay, azimuth elevation rotator. If you're fairly well heeled, you can go out and buy a ready-made one like this. I used to have one once. I sold it at Gosford. Why on? There's the azimuth rotation impression. It turns around in a horizontal plane or on a vertical axis. And then, of course, the elevation will allow it to rotate on a horizontal axis like that, and you can point an antenna further up in the sky or down to the horizon or even down to ground. There's another Azell one, well established in the marketplace one. So it's got the two directions similarly catered for. These are really expensive, a couple of grand, something like that. So that's the Azell mount. Now the equatorial mount is an interesting thing. So what you think of our half part of the world sitting over a funny tilt, like just imagine the axis that the Earth is rotating around, and it's gradually working its way around, and it's fixed in that way, and so wherever it is around the sun, it's always rotating in that on an axis that's parallel to that. Now, here we are over in Brisbane. If we've set up an antenna that we want to rotate from left to right, and if we set it up on a flat, well, we think the ground is flat where we live, it's not the same angle as it is in other parts of the world, and not at the same angle as the axis of rotation of the Earth. So I think that's called declination, is it not? Right. Yeah, pretty sure. So that angle, of course, is equal to the latitude, which is 28 or so south of the equator. So the angle between that and the axis of rotation is about 28 degrees. But if we wanted to focus on something that was located around the equator, we wanted to move between different ones, we'd have to, if we just rotated it around on the first picture, you'd get the beam would be off the plane of the equator only most of the time. But if you actually rotate it on the axis parallel to the axis of rotation of the Earth, then you could track something that's actually on the equator. Geostationary satellites is one. The sun is fairly constant. But even the moon is not exactly there. Moon wobbles around and it's close, but it's a little bit off. The astronomy fraternity love these equatorial mounts because they can fix their gaze on something that's so far away and then rotate the antenna and just get a long shot of it. It stays in focus. So we're trying to rotate that way. And we're also trying to rotate up and down. So the equatorial mount does all of this and more complicated than the Azel mount. I met for the first time in my recent trip to Scotland Roger, PM4PMK, and he has a 3.4 and 1296 antenna, which is on an equatorial mount up there in Scotland, which seemed like a reasonable solution for him because of the location a long way away from the equator. It worked fairly well. Well, I think I've explained that mostly, except that if you actually go back here, you actually set that second one there really accurately to be parallel with the axis of rotation of the Earth, called a polar mount. And it's actually the precision situation that astronomers love. So that's those two mounts. Mechanical considerations: worm drives versus screw jacks, wind loading. See what they are. And whatever you're doing with these antennas and things, you're looking at mechanical challenges. And some people retreat from them and some people rise to the occasion. But if you go and buy ready-made things, that's okay. You've got the money to spend. But this VK3NX Charlie in Greater Melbourne down there got this large dish, and he works at pointing with screw jacks, or linear actuators, I think they're otherwise called. Quite clever, stable mechanics that are able to be adjusted electronically. I just briefly present that there is whatever mechanical solution you come up with, it's got to be strong and able to withstand the buffeting of the wind, because if something gets loose there, it could be threatening people as well as material things around where it's located. Loading. A whole lot of points that you need to consider. It's not always the same. What is the prevailing wind of speed and direction? What are the wind gust extremes at your location? And it's all probabilities, this, because I think the main way of thinking about this is what is within 80% of the extremes that you could get in this area. 80% is a fair range of possibilities. How big is the dish? How high is it above the ground? Makes huge difference to how hard it is to hold in place when the wind is blowing. Is the dish surface solid or perforated, or is it a grid pack? They all have their difficulties in terms of the solid, of course, will be blown around by a light wind. Perforated mesh dish will withstand a bit more, but once you get above a certain amount, the mesh dish, depending on the mesh size, will seem to the wind really looking like a solid dish. And then finally you get to the grid pack, which probably will let most of the wind through. Still had some wind area. Just think about it, the dishes are not the same from every angle, and the wind might be blowing from a certain angle that may blow the dish like a sail. There's a good habit of parking a large dish when not its use, parking such that it looks like a big saucer pointing directly up into the sky or during bad weather. I once visited the Australia telescope in Narrabri. They had 6 or 8 huge dishes on a big railway line. They could position them wherever they wanted to, but every one of them was monitored, and they had wind and turbulence monitoring equipment and also weather forecasting. And whatever the scientist was, even if they were in the middle of something really important, if the wind was coming up, everything just had to be turned off and go back to parking mode, which I thought was very cautious. Another thing to consider is how many antennas are on the antenna support structure. And what is the antenna support structure designed to withstand? Do you know? So a whole lot of things to consider rather than just getting an antenna and a tower and putting it up. That's wind loading. So by look and see monitoring where a dish is pointed, we're really looking at having a sighting little telescope or some other method like that. Here's a Rex on the K7MO pointing to this group of onlookers about to his little sighting telescope that looks through from there to the front, and that's perfectly aligned with the beam of the 10 gig dish. But if you look at the next picture, that little hole is where the sighting thing is coming through. So that's a beautifully designed pointing mechanism. And the other interesting thing is that if he's signing up on the sighting on the sun to look at sun noise, obviously you don't look through here. But what you do is you get a piece of welding glass or something like that, and an image of the sun is seen on the back of the sighting thing. You can actually see when the dish is pointed exactly at the sun. Pretty clever. Now, a fellow that both Roger and I have visited in Bathurst in the country of New South Wales, in the country area of New South Wales, there's a 5 metre big dish out there, and he operates on 1296 you can see the square nature of a septum feed there at the feet. But he does have electronic monitoring, like with potentiometers and other methods, but he does also have a little place where you can get up on the ladder behind the dish and look through a hole that's somewhere on the side here, or a little gap in the mechanism. And somewhere out here on this is a little piece of wire with a loop on it, and he's carefully located that so that when you see the moon lined up with this loop and the hole that you're looking through, the dish is perfectly pointed towards it. So something like that. No, it's just looking through a gap in the mechanism. Yeah. So anyway, that's the look and see method. I mean, I'm guilty, and many amateur radio operators are guilty of saying, well, I know where you are. You're over there on that hill. just point the antenna towards that hill, and then you hear them weakly, and then you just optimize the positions. Doesn't have to be exact control all the time. But if you go back to, you can have electronic monitoring with the readouts on the LSL meter, antenna rotator control box or something like that. Or you can have it all fed back to a computer which knows where you're trying to point and computes the elevation, the azimuth and elevation things required, and then will actually drive your dish to where you want to go there. Seems like a wonderful way of doing it, but it's also giving up some of the personal satisfaction that I did it. Anyway, that goes for a lot of things in not just amateur radio, but life. So at the end of the day, we're very interested in pointing the dish at the right direction, because if it's not, then we may not hear anything. This picture we used from the previous talk, part 1. This is what we're aiming for. We've got something that's capable of pointing something in such a well-defined and single beam, or basically a very well-defined beam in one direction. And we want it to work. We want it to work for us. So we've got all of these pointing things and all the things we've been talking about here. But remember, in the previous list, we went through a list of everything that needs to be optimized and considered. That list is huge. Illumination, spillover, feed blockage, phase error, where is it located, fraction, polarization shift, blockage by feed supports, surface error in the parabolic reflector, and loss, and VSWR. You get all that right, you're doing very well. And so I wish you well to that end, and that's the end of my 2 talks on parabolic dishes. Any questions?
Yeah, Mike just joined us. If you look up.
Oh, good day, Mike.
Oh, yeah. Sorry I'm late.
Did you see any of the talk?
I saw just the last few minutes, I'm afraid. I was very disappointed, but I was unavoidably detained.
All right. Well, Andre, is it going to be recorded? Or has it been? All right. So be able to look at it on the Brisbane VHF group website sometime soon.
That's great. Thank you very much.
I have a little question. I've got with those feeds from that RF hand design, where they've got the 4 and 5 feet, the one little compartment. I'm having issues now with 2 and 6. Now that I can run 6 meters with what's it called, splatter or whatever you want to call it, over the top of one or the other band. Normally 6 splatters on 2. But is this, if you've got one or more radios connected to such a feed, would it interfere in any way or damage in any way? Let's say
absolutely. It's huge coupling, probably only 10 dB or something down or something like this. Huge amount of power is picked up by the other rings from the one you've got energy going into. So every one of those needs to be terminated in a suitably large 50 ohm resistor. Probably means there's quite a lot of your power is being absorbed into resistors at the antenna. But you can't have one live and the other one. If you want to do crossband or something like that, you can't do it with those feeds.
Thank you for that, because I've been looking for some smaller idea so I can use one band, one disc, and I've been using different feeds. Seems to be okay, but as long as I'm running the radios as I do. But if you like that one, well, okay, that's done what I need to know. Thank you.
That's all right. Good question.
So on that, then, Doug, can you place the rings a precise distance from one another and use that to your advantage to reduce?
Yeah, there will be a minimisation of coupling, but just think about it. They're so close to each other that it's going to be large coupling anyway.
It all rings up within the near field of each other. So the coupling is quite substantial. Yes. It's the field in there is quite strong.
All right, Bob's question. Could you hear Bob's question, John? And it's just related to more an observation as to how much effort you have to put into mechanically stabilising a dish when you've got it outside in a practical location. You know, if you're trying to steer it, you've got to actually be able to steer it and then leave it where it is. It doesn't wobble in the breeze. Rattle and keep the chooks awake at night.
We had our dishes up on the weekend around about 8 metres roughly. 596 grid pack, 2.4 gig, 5.8, and we didn't put 10 gig up because we don't know how to put a big box up the top. And we had minimal, it was quite blowy, and we had stays out, 4 stays out of the top of the tower down, big down, and there's very little movement at all, and we could rotate it from a rotating system on the end of the mast. But we can't do anything else other than rotate. Can't get in the other angle other than just being level with the vehicle we got.
Yeah, well, that sounds like you're quite successful there, but compared with large dishes that people might be putting up for EME, you're only using small dishes and the amount of windage much less. But what you've done is solve the problem that you hear about every now and again. People that have been doing portable microwave amateur radio for many years all have stories of the gust of wind, the unexpected gust of wind blowing the dish over.
Yeah, I think the 5.8 gig was one of those around about 400 millimetre diameter, and it's solid. wasn't a grid pack, but it wasn't affecting it, and it was quite blowy around about lunchtime onwards. We're coming around 15, 20 knots, so we were quite happy with the result. We went out specifically to do that, so for the next field day to make sure that we could get the dishes higher. If we went to Mount Cravat, for instance, get them all away from the observers, so that we don't have any issues with somebody saying, "Oh, these people are running microwave, that knew about it, and job you into whatever." Keep the insurance happy.
Yep. Something I just thought of in relation to. Oh yes, the difference between that guide mast that you described and a tripod. And a tripod, unless it's tied down itself, does have a tipping point.
Sorry, can you just recap the benefits of the Cassegrain?
Benefits of the Cassegrain. Might go back nearly right to the beginning, isn't it? The benefits of the Cassegrain really are in effectively illuminating a deep dish, which can be a big advantage to use a deep dish rather than a shallow one, as far as spillover and getting illumination right. Collins, I was about to say that too. Collins emphasising that the minimisation of feed line loss. These dishes there, they're talking to the Voyager 1 and Voyager 2, and they're a couple of billion kilometres away each. So it's only on 8 gigs, not like they're on 40 gigs or something. But minimising all losses is a good way to do it. And the other thing is that it's very efficiently illuminating that dish. You go back to the previous image here. Just imagine any rays coming out from the feed wider than that, they're just lost. If this one catches just here and then bounces across the edge there and then bounces out like that, it's a very efficient way of doing it, and you can fairly evenly illuminate this, which means you're fairly evenly illuminating all of these other locations as well. Mathematics is
VK3XPD.
Yeah.
He did a lot of experimentation with Alan and young Matt on 3D printing hyperbolic reflectors and dishes, and I think the article was in one of Dubas magazine.
Mm-hmm.
And they 3D printed them and then sanded them down and then just put tin foil on them.
Yeah.
And they work like a treat.
Yeah. Our local millimetre wave guru, Stefan, VK4 CSD, has actually taken a teaspoon, different, or a sugar spoon or something like that you can buy from a domestic place, and located that in front of the feed. Used that as a way of illuminating a Cassegrain way, and it worked. He doesn't know whether it was optimal, but it certainly seemed to work quite well. Just imagine the gain of that thing at 8 gigahertz with 73 metre diameter, 73 metres, and a fairly efficient feed system. Could I just describe an interesting thing that I saw when I visited the Australia Telescope many years ago, probably 25, 30 years ago. No, it wasn't the Australia Telescope. It was a big OTC station at MRE. This Cassegrain reflector was located on a spindle that could be driven by a motor, such that this spins around horizontally, but the reflector was slightly off center, so it's sort of wobbling around like this, and that had the effect of producing a continuous through the peak all the time of the illumination, and they could see on their instruments and things that the dish needed to be repositioned or recalibrated or something like that, because this thing was a constant, slightly 1 dB down, and it was in some positions like that, and they could measure and see if it was pointed correctly, and quite clever. I think that's probably about the limit of the conversation, is it, everyone? All right. It's all right. Happy to help.
Yes, thanks very much, Doug.
Well, good on you.